Welcome to Mrs. Z's Chemistry. In this video, we will learn molecular geometry and something called the VSEPR model. First, let's review the octet rule. Elements form bonds so they have access to 8 electrons. We are going to be looking at just the elements in the main groups because these are the ones that make covalent bonds. The main groups, of course, are the first 2 columns and then the last 6 columns on the periodic table. They're often labeled 1A, 2A, 3A, and so forth all the way to 8A. You can also think of it as the main groups are just the S and P blocks from the periodic table and not the D or F blocks. Of course, there's always exceptions to every rule, just like with the octet rule. So, obtaining an octet is the reason for bond formation for many of these compounds formed by the main group elements. However, hydrogen only has 1 electron to share, and so it usually only makes 1 bond. We don't ever put an extra lone pair or a second bond on hydrogen as it doesn't have any more electrons to share. So we say that hydrogen fulfills a duet rule. If lithium were to make covalent bonds, lithium would also have a duet rule, but lithium is a metal and usually creates ionic compounds. Beryllium and boron also have less than an octet. They have so few electrons. Beryllium has 4, and we should have a B here for boron. Boron only has 5 protons and beryllium 4 protons, so they both have a difficult time attracting 8 electrons around them, so they often only make or have 4 electrons shared around them or 6 around them for boron. Of course, there's also something called an expanded octet, and those are for the elements in period 3 on the periodic table or lower on the table. They are large enough to sometimes have more than an octet, either 10 shared electrons or 12 shared electrons, and we'll see some examples of those in this lesson. A chemical bond is the force that holds 2 or more atoms together, and it involves only the valence electrons, which, if you remember, are the electrons in the outer shell. So bonds form between the valence electrons, and they do not form with core electrons. All right, so now that we've reviewed the octet rule, let's learn how to determine the molecular geometry, which means the molecular shape of the molecule, from a Lewis structure. So first, let's pause the video to draw the Lewis structure for CO2. Here is the answer. Here's the Lewis structure for CO2. Carbon is the central atom, and it has 2 electron domains around it. Well, what's an electron domain? An electron domain is either a bonding pair of electrons, so a single, double, or triple bond, or a non-bonding pair, which we call the lone pairs of electrons. Electron domains will try to get out of the way of each other as much as possible because the electrons repel each other. So carbon dioxide has a linear structure because the 2 electron domains around carbon are going to spread out as far away from each other as possible, which will end up forming a straight line between the 3 atoms, the oxygen, the carbon, and then the other oxygen. The bond angle for this structure is 180 degrees. All right, pause the video to draw BF3. Here is the Lewis structure for BF3. Boron is the central atom, and it has 3 electron domains around the central atom. This one, and this one. We do not count lone pairs on the attached atoms. We only worry about what is around the central atom. There are 3 things, or electron domains, around boron. So the Lewis structure is actually, it's okay to draw the Lewis structure like this with a T shape, but the actual shape of the molecule has more of a Y shape. If you imagine that those 3 electron domains of the attached atoms, the fluorines, they're going to spread out as far away from each other as possible. And all 4 of these elements, the boron and the 3 fluorines, are all in the same plane. And we call this trigonal planar. The bond angle is 120. Imagine a circle which has 360 degrees. Cut that circle into 3 even paces, and you have a bond angle of 120. All right, now let's draw the structure for CH4. Pause to see if you can draw this simple structure. Carbon is the central atom, and there are 4 electron domains around the central atom. When these 4 domains spread out away from each other as much as possible, they create this shape in a 3D shape here, and we call it tetrahedral. We say that this atom, the central atom, and this atom, they're all on the same plane, but then you have one atom, this one back here, that's going back into the plane of the board, and then this one's coming out into the front of the plane of the board as well. All right, so let's review our electron domains again. One electron domain is a single bond, or a double bond, or a triple bond, or a lone pair of electrons. Each of these 4 things that I have listed in bullet points all count as only one electron domain. A double bond, even though that is twice as many electrons, that still counts as only one domain. A triple bond only counts as one domain around the central atom. So this is called valence shell electron pair repulsions. This is the model that we call the acronym VSEPR. We can pronounce as VSEPR. And it says that the electron pairs, whether it's bonding or not, will repel each other, and they will get out of the way of each other as much as possible. And this is how we can predict the shape of the molecule or the geometry of the molecule. There's a different degree of repulsion between the different pairs that we could possibly have. If you have 2 bonding pairs of atoms, like 2 attached atoms next to each other, we call that kind of like the default amount of repulsion. And whether that's a single, double, or triple bond, they're going to repel the same amount. If you have a lone pair of electrons on the central atom next to a bonding pair, that's going to repel a little bit more, and then 2 lone pairs next to each other repel the most. But it doesn't really change the structural shape as much of the atom or of the molecule. All right, so we're going to look at 2 different types of geometry: electron domain geometry as well as molecular geometry. First, let's look at the electron geometry, and this is based on the number of electron pairs that surround the central atom, whether they are bonding or not. So we use a symbol of A, which it designates the central atom, and the X designates how many electron domains are around the central atom, whether it's a lone pair or a bonding pair. So here's a nice little chart to show this. If you have AX2, that means you have a central atom and 2 other electron domains on the central atom. If those 2 electron domains get away from each other as far as possible, they create a linear structure with the central atom, and the bond angle is 180, and we have 2 examples. We'll be drawing lots of examples in a moment here. If you have 3 electron domains around the central atom, the symbol is AX3. We call this trigonal planar, bond angle 120, and then here are a couple of examples. AX4, like we've learned, is called tetrahedral, bond angle is 109, and then here's 2 examples that, again, we will be drawing in a moment. But first, let's look at the molecular geometry. So now we're going to look at those electron domains and differentiate them. The A will still mean the central atom. The X will now designate just the number of bonding pairs, or the number of attached atoms, you can think about it. E is now going to designate the number of lone pairs on the central atom. We are only concerned about what is on the central atom. So now our chart looks a little bit different. If you have the parent structure of AX2, the electron geometry is linear, and if both of those electron domains are attached atoms and you don't have any lone pairs on the central atom, then the molecular geometry is still called linear, and our example is CO2, which we've already seen. Let's look at AX3 as our parent structure. The electron geometry is called trigonal planar. If all 3 of those electron domains are attached atoms and you have 0 lone pairs on the central atom, the molecular geometry still has the same name as the electron geometry, trigonal planar, and our example is BF3 that we've seen. But if we have one of those attached atoms is replaced with a lone pair, so we only have 2 attached atoms and 1 lone pair in the central atom, we call this bent, and I'll show you the structure in a moment, and our example is SO2. So you see the symbol is AX2E because we have 2 attached atoms, and the little subscript 1 is implied, but that E comes from only one lone pair on the central atom. Now let's look at AX4. We have 4 electron domains around the central atom. It's called tetrahedral. If you have 4 of those, or all 4 of them are attached atoms and 0 lone pairs, you still have the name of tetrahedral, and the molecular geometry name and example and symbol is the same as the electron geometry. But you replace one of those attached atoms. Now we only have 3 attached atoms and 1 lone pair on the central atom. We call this trigonal pyramid. And then if you have only 2 attached atoms and 2 lone pairs, we call this bent. And you can see that the symbols are changing, AX3E or AX2E2. It still has 4 electron domains around the central atom, but some of them are attached atoms and some of them are lone pairs. So let's draw the structure for SO2 and determine its electron geometry and the molecular geometry. So we have 18 valence electrons total from sulfur and 2 oxygens. We have a sulfur in the middle. We have our 2 oxygens on either side. This is so far only 16 valence electrons that we've placed, so we have to put the 18th, 17th, and 18th electrons as a pair on sulfur. Oxygen cannot have an expanded octet. Because both oxygen has a full octet right here, we have to put that the pair, the last 2 electrons, on sulfur, because sulfur can have an expanded octet. So here's our structure. SO2 has 3 electron domains around the central atom. Each bonding pair, that is right there, that is 1 electron domain. Here's a second electron domain, and the lone pair counts as a 3rd electron domain. So therefore, we have a trigonal planar electron geometry, because this would be AX3 for our electron geometry, but the molecular geometry takes into account the fact that there's only 2 attached atoms, and that lone pair, which is sitting right here on sulfur, is bending down the 2 attached double bonded oxygen atoms. And so it is no longer a linear structure, but this is why we call this a bent molecule. It looks like the molecule has been bent. Now let's draw NH3 and determine its electron and molecular geometry. Pause to see if you can draw the Lewis structure for extra practice. Here's the Lewis structure. You can see that nitrogen is the central atom, and it has 1, 2, 3, 4 electron domains around the central atom. So its electron geometry is AX4, tetrahedral. However, when we're looking at the molecular geometry, this is where we're going to look at AX3E, because one of those electron domains is a lone pair and not an attached atom, and that lone pair is sitting right up here, and it's going to bend these 3 attached atoms down out of the plane of the central atom. This looks like a pyramid, which is why we call this molecular geometry shape trigonal pyramid. This bond angle here says 107, but we usually also describe it as just less than 109. The bond angle for tetrahedral is 109, and the bond angle for AX3E or trigonal pyramid is, we often just say less than 109. On a quiz or a test, I would accept just 109. All right, let's draw the Lewis structure for water. You can see that oxygen is the central atom and that we have 1, 2, 3, 4. 4 electron domains around water, around oxygen. The electron geometry is still AX4 tetrahedral, but the molecular geometry is now AX2E2, which we label bent. The 2 lone pairs are sitting up here on oxygen on top and bending down the hydrogen atoms. So the hydrogen atoms are not in a straight line with oxygen, so it's no longer linear, but we have a bent shape. We just have 2 more electron and molecular geometries to look at here. The first 3 rows on this chart is what we've looked at. We've looked at all those examples and drawn all of those molecular examples here. Now let's draw 2 more, or look at 2 more. We have AX5. So if you have 5 electron domains around the central atom, we call this trigonal bipyramidal. You can remember this because tri equals 3, bi equals 2. Tri plus bi, 3 plus 2, is equal to 5. The bond angles, we actually have 2 bond angles for this one, 90 and 120, and you'll see why we have 2 different angles in a moment. A good example, PCl5. So let's actually look at the slide for that one. So when you have a central atom and you've got 5 atoms here, let's look at how the bond angles are made. First, let's look at the central atom, and then 1, 2, 3. These 3 attached atoms are all in the same plane. So that kind of, if you were to ignore the top and bottom atoms, that kind of looks like a trigonal planar shape. That's where the trigonal comes from, and that's where the 120 bond angles. If you imagine the bond angle from this atom to that atom is 120, or this atom to this atom is 120, this atom to that atom is 120. So that's cutting your circle into 3 even shapes, and you've got bond angles of 120. But when we have an attached atom sitting on top and on bottom of this atom, of the central atom here, then we now have bond angles of 90 right here, from the top to any of the sides or from the bottom to any of the sides. That's where the 90-degree angle comes from. So this is why this molecular structure has 2 bond angles. And PCl5 is a great example of this, where you've got phosphorus in the center, and then you've got chlorine atoms, 5 of them, all sitting out here. And we could draw the Lewis structures that way. Each chlorine atom would have 3 lone pairs on it, but we've got 5 attached atoms here. So now let's go back up here and look at the AX6. We have 6 electron domains around the central atom. We call this octahedral, and I know that might sound weird because oct usually means 8, like an octagon has 8 sides, so you might think octahedral should have 8, but in fact it does have only 6 attached atoms, and we'll look at why it's called octahedral in a moment. The bond angle is 90, and our example is SF6. So let's go to the slide for the octahedral molecule. Here's your central atom, the A, and then you've got all these attached atoms, 6 of them. So to look at the bond angles, let's ignore the top and the bottom atom really quick. And you have 5 atoms now, all attached together, and they're all in the same plane. And then you've got the top and the bottom. So if you just look at the sides again, we have 90-degree bond angles right here between this atom and this atom, or these 2 atoms, or these 2. Now you're going to cut your circle into 4 pieces, and that's how 360 divided by 4 is 90. But then also with the top atom to any of the sides, that is a 90-degree angle, or the bottom atom to any of the sides, that's also a 90-degree angle. So we only have 1 bond angle with this molecule. If you were to close in all of the sides, like here's a triangle, and then close in this side, and then close in this side of this shape, you would have 8 faces on this particular shape. Imagine the central atom kind of somewhere in here, and then you've got the top atom, the bottom atom, then all 4 of the side atoms, and this becomes an octahedron, which is why we call it an octahedral molecular shape, because there are 8 faces when you have 6 attached atoms to the central atom. So here's another way of looking at this chart right here. The steric number is what I've been calling electron domain number, when you have 2 electron domains, or 3 or 4 or 5, 6 around the central atom. And then across the top here, the rows look at either having 0 lone pairs, or 1 lone pair, or 2, 3, or 4 lone pairs. Now in this course that I teach, you can see everything that's enclosed in this red line here is going to be what I might test on or quiz on. These structures out here get a little more complicated, and we look at those in AP Chemistry more specifically. So you can see that when you have 2 attached atoms right here, you have a linear shape, and the bond angle is 180. When we're looking at 3 electron domains, you could either have 3 attached atoms, bond angle is 120, name is trigonal planar. You replace one of those attached atoms with a lone pair, and now you have a bent molecule. Bond angle, we say, is, notice this is a less than sign, less than 120. We often just still call it 120. When you have 4 electron domains, you could have all 4 attached atoms and have a tetrahedral molecular geometry. Or you could replace 1 with a lone pair, and you've got 1, 2, 3 attached atoms called trigonal pyramid. Or you replace 2 of those atoms with lone pairs, and you have now a bent molecule. Bond angles, we say, are less than 109 for when you start replacing the attached atoms with lone pairs. Then if you have 5 electron domains, you've got all 5 attached atoms, trigonal by pyramid. The bond angle is 90 and 120, and that's the extent that we're going to look at. However, you can start replacing the atoms with 1, 2, or 3 lone pairs, and your shapes look a little bit different. And so the names for the molecular geometry are different as well. Seesaw, T-shape, and linear. But we don't need to learn those for this course. 6, electron domains. If you have all 6 of them are attached atoms, we call this octahedral with a bond angle of 90, and that again is the extent that we will look at for octahedral molecules. But if you start replacing the attached atoms with 1 or 2 or 3 lone pairs or 4 lone pairs, your shapes for the molecules begin changing a little bit. So the name changes: square pyramid, or you've got a square planar, T-shape, and linear.